Hello everyone, welcome to 2023 free response problem question number 4. This is asking us about do you know how to prepare of a buffered solution? So when you see this trend from the recent 3 years, 2022, 2024, we see the titration of a weak acid with a strong base problem is presented. And the concept of buffer, the half equivalence point is the region of buffered region. So we are applying the Henderson-Hasselbalch equation, which is the buffer equation, to calculate the pH or reading the graph to find the pH. That was a core concept in those problems. And this problem is also related with the concept of buffer. You know, the buffer solution is very essential for understanding biochemical reactions, all those reactions that is happening in microbiology and medicine, biochemistry, biotechnology. They are all geared toward about buffered solution. We need to have a stabilized pH condition to have, like really stable chemical reactions, stable the system. So we need to have a really great understanding about this buffer system. And let's get started. So our system is given with a weak base, methylamine, and this is added, and it's conjugate base, methyl ammonium ion. So let me draw your attention to the structure of methylamine. Here, the nitrogen has a lone pair, and nitrogen with a lone pair. In this case, we have here one methyl group, one alkyl group right there. This is called a primary amine. And primary amine, secondary amine, tertiary amine, the nitrogens all have a lone pair. This lone pair makes it work as a weak base. So in aqueous solution, hydroxide ion is a strong base. So anything that contains hydroxide ion, such as sodium hydroxide solution, potassium hydroxide solution, or I mean potassium hydroxide solution, or calcium hydroxide, barium hydroxide solutions, they are all strongly basic solutions. Here, as you see, the case of weak base. Weak base is many of them they are nitrogen compound. And when this one is added with the combined with strong acid, for example, here I drew hydrochloric acid, and it becomes a weak base. A conjugate base is a weak base. Conjugate acid. I'm sorry, this one is conjugate acid. This conjugate acid is a weak conjugate acid is weak acid. What we need to remember is Ka value of the conjugate acid and Kb value of the base. When you multiply it, it is same as Kw, which is dissociation constant of water, 1.0 times 10 to the negative 14 power at room temperature. And so when you read this one again, write this one again in logarithmic expression, pKa value of an acid and its conjugate base pKb value, when you add up, how much is it? Yes, it is 14.00. pH plus pOH is 14.00 at room temperature. Also pKa and pKb, when you write a conjugate pair, their pKa value, pKb value, when you add up, it is 14.00. So let's keep in mind these properties and work on this problem. And buffer is prepared by equal amounts of this base. Like methylamine is in aqueous solution. So methylamine is a liquid. So we are preparing this one, put this one into a water and making a solution. And it'll be well dissolved into the water because the alkyl group is small, one carbon compound, and the nitrogen will be forming hydrogen bonding with water, well dissolved. And its conjugate base is prepared from salt. The salt, as you see here, many of them is solid. So there, methyl ammonium chloride is prepared as solid. So this student prepared a basic solution using 25 ml of 0.1 molarity of the solution, and which will be providing 0.00250 moles of methylamine. Now calculate the mass that contains same mole number of the conjugate salt, which is methylammonium chloride. In this case, let's analyze it. It is composed of carbon, hydrogen, nitrogen, and chlorine. Let's count. Analyzing the compound and reading the number of atoms in the compound is important concept, especially at the introductory level. So I see one carbon here, and I see 3 of carbons in methyl and 3 of carbons in ammonium, total 6, I mean, not carbons, hydrogens, let me correct it, and 6 of the hydrogens, and 1 nitrogen found, 1 chlorine found. Let's go to the periodic table. Let's find the information. For example, for carbon has 6 protons, atomic number 6, and then 12.01 AMU. And then let's multiply the number of atoms for the compound. And in this case, we have 12.01 times 1 plus we have 1.008 AMU of hydrogen. We have 6 of them plus and 14.01 AMU of nitrogen times 1 plus chlorine. So among halogens, chlorine is the most frequently used. This one 35.45 AMU. We have 1 of them. So when you add up, it is 67.518 AMU with proper number of suffix 57.52 grams per mole. Once you have this molarity, I mean molar mass, let's multiply with the mole number, required mole number. So let's write 0.00250 mole is required. And let's write the molar mass. Then mole is given, so we need to write mole number bottom and gram top. We are converting mole number to grams. So 1 mole had 67.52 grams of mass. And then mole cancels out. We have now mass, which is 0.169 grams of methyl ammonium chloride. Okay. Now, once you do this one, let's work on problem B. And this is asking about experimental steps to prepare this buffer. Fill in the blanks for preparation of the buffer. First, when you look at the step 2, it is saying place a solid in the 50 ml beaker. It meaning that we need to measure out the solid. And the salt, which is methyl ammonium chloride, is a salt. So then step 1 must be measure out 0.169 grams of the methyl ammonium chloride. Where we need to use weighing boat, or here weighing paper is given in the example. So then let's write it using a weighing paper. So in the lab, chemistry lab, we are using weighing paper or weighing boat, and onto an electronic balance. We call this one electronic. In this case, we need to read up to third decimal, and then most likely the balance will be an analytical balance that gives us a power to read up to 4 decimals. And number 3, clean the burette and rinse with distilled water. So we are preparing the burette. Reading the burette, preparation and conditioning is very important. Now number 4, so here we are putting 50 ml beaker. 50 ml beaker, we have prepared this solution. I'll place the solid. So not yet. So let me erase it. Erase this one. So we have only solids remaining at the bottom, and then from the burette. Now let's fill it up, and this one will be liquid. So we'll have drop by drop put this one into the beaker, and then we'll be mixing them up. So then we need to fill the burette with the solution, with the zero point 0.1 molarity of methylamine solution, CH3NH2 solution. And when you add number 5, we'll be using the burette to add 25.00 mil. Remember, the burette allows to read up to second decimal, so do not forget 25.00 when you write the answer. For example, when you are asked to write the answer using the burette, and 0.1 molarity of methylamine solution to the beaker, mix well. So typically we are adding in this case, the amount of the salt is small, 0.169, so we can just swirl the beaker and mixing and dissolving the salt, or many times we'll be adding a magnetic stirring bar to mix it well, and then check the pH with the pH meter. Okay, now let's move up to the next problem. A buffer that contains, already covered this one, let's move to the next one. And KB value, this on base dissociation constant of methylamine is 4.4 times 10 to negative 4. Here again, the Kb value is much less than, smaller than, 4 orders smaller than 1. And this is a weak base, okay, because this nitrogen is lone pair, and nitrogen lone pair, primary amine, secondary, tertiary amine, it is always used as a weak base. And the pH of the buffer was 10.64. Now student prepares second buffer. In this case, the amount of the base and the amount of salt is now cut down to half. Is the pH of the second buffer greater than, less than, or equal to the pH of the first buffer? First, in this case, remember the amount of the base, like 25 initially, 25 mil of 0.100 molarity of the conjugate acid. Like, let me erase it and then write it again. So then it is 25 ml of the solution. So then the CH3NH2 was used, but now in second the volume is same, but the concentration is now half of the solution. And also initially we were using the amount of, as we calculated before, 0.169 grams of methyl ammonium chloride was used. Now half of it is used. Then what will be the pH? In this case, this one is asking about Henderson-Hasselbalch equation. So pH is calculated by pKa value of the acid plus logarithmic of the acid under the conjugate base, like this way. Here pKa is a constant, so pKa doesn't change. And let's think about the ratio of the acid and its conjugate base. And both of them is half now. The volume is same, but the concentration is half. So then mole number is half. Mole number. So mole number is eventually go to molarity. So this is half of the initial value. Initial, let me write initial. And then, the conjugate base in this case, also the acid is half. The amount is half, meaning mole number is half. So it is mole number initial, and then this one cancels out. It is same. The ratio doesn't same. So because the ratio is the same, pH must be the same. Don't change. Okay, remember pH is pKa plus logarithmic, like the conjugate base over a acid concentration molarity, and then when you make them both of them amount is half, then the ratio doesn't change. As a result, pH is the same. As you see this one, this is really trend of understanding, helping, asking us to understand. Do you understand the concept of a buffer? And buffer is extremely important in chemistry, especially as you many of the students who take chemistry, they are pre-med students. They are very interested in to go into medical field or nursing or some those areas. And because our body is basically composed of buffering system, we need to understand very well of the buffer. And so this question, let's have time to thoroughly understand how to work on those problems. Thank you. I'll see you in the next video.